these are the topics we have covered. We've actually covered a lot, alhamdulillah. Okay? In terms of design, we covered divide and conquer, dynamic programming, and greedy. And then in analysis, we covered all the major analysis techniques: asymptotic, probabilistic, and amortized. And last lecture, we covered recurrence relation, master theorem, and Akrabazi. So, what remains of the course I consider is fun and light stuff. And it's also entertaining, and it's also a topic of interview questions. So I hope that you will benefit from it, and you will find it more perhaps entertaining than anything we have discussed before. So this is what remains. We are going to just cover one last little topic. I know you're probably like breathing heavily now and saying, "Oh, finally I got done with analysis," but we just have to discuss something related to analysis, and by that we completely finish analysis. And then we're gonna see a special class of algorithms that are related to search engines, and these are called ranking algorithms. And we'll talk about their design because they're very interesting and different from anything you have seen before. And I conclude the course with a number of data structures for the purpose of enriching your background in data structures and making you think more about data structures. And because these are very common topics for interview questions. So if you're not going to take any advanced data structure course in the future, at least you have seen the ones that you really should see before you graduate from college with a computer science and engineering degree. So let's start by finishing the analysis part, just to wrap it up. We're going to talk about a topic called lower bounds of algorithms. So what are these lower bounds of algorithms? Okay. Now, let's say someone invent an algorithm to do a specific task. And he says, okay, I've done a great job by coming up with this algorithm that is, say, of O of n log n. Now, and he says, no one will ever develop an algorithm that is better than mine. Now, this is a very bold statement, because maybe someone will come in the future and develop an algorithm that is faster. So if his algorithm works in n log n, maybe someone will come and design an algorithm that is in O of n, or O of log n. Okay? But he says, no, I can prove to you that there will never be a solution faster than mine. Wouldn't that be interesting as a statement? Wouldn't you be interested to learn how can he be so bold and has the courage to claim that? Okay? And it turns out actually he's not showing. It turns out actually that this is an activity within the computer theory group that they always get engaged in, which is, can we do better? Should we invest our time to do better? Or should we be satisfied with what we have reached up till now, because we have a proof that we will never be able to do better? Okay? And there's a difference between claiming that no one will be able to invent something better versus you have a proof that no one will be able to invent something better. So if you have a proof, that's very interesting. Okay? And this is what this topic is about. So again, when we talk about lower bounds, remember when we discussed omega and theta and O, we said O is worst case, omega is best case. So here we're really talking about the best case. And the question is, can we go better than the best case for a specific algorithm or a specific class of algorithms? Okay? Now, why this is interesting? Because you could always get worse by just being a little bit more unintelligent in your approach. But to be better, you have to be really unique in what you do. But if someone tells you there is a proof that you'll never get better, then you don't need to waste your time. Okay? And this type of question again is interesting from a theoretical point of view, because if we can prove that we cannot go do better, then we should not look for a better algorithm. Okay? Now, this is actually very hard to prove. This is not something simple, as you probably already kind of guessed from your theory courses. When I say that I'm going to prove that no one will be ever be develop an algorithm that is better than this, and I state some asymptotic order, I must have went through a very deep thinking process that covers all possible cases, and I concluded from that there will never be better. Okay, so let's see how we can do that for something you're familiar with, which is sorting. Okay, sorting is a very good example to start with here, because you've all learned sorting since your early computer science courses. You've seen a variety of sorting algorithms. So going back to your early computer science, you must have seen bubble sort and selection sort and insertion sort, and you should have also seen variations of these sorting techniques in the tutorials or sections. And in this course, you have also seen something else. You have seen merge sort and you have seen quick sort as examples of divide and conquer. Now, if you remember, merge sort and quick sort is in O of n log n. Selection sort, insertion sort, bubble sort are all n squared. Obviously, n log n is better than n squared. The question is, can we do better than n log n? Should we be interested in developing a sorting algorithm that is better than n log n? Now, if someone has proved that you'll never be better, then you don't bother. And this is again the idea here. So, before I go into the discussion, we have to classify sorting algorithms. There are two types: algorithms that sort by comparing values, and algorithm that sorts by not comparing values. And this might sound a little bit ridiculous, because how can you sort a set of values if you're not going to compare them? I will show you one soon. Okay? Now, but let's focus first on comparison-based sorting algorithms. Okay? Now, everything you have seen up to now is actually comparison-based, including selection sort, insertion sort, bubble sort, quick sort, and merge sort. They're all classified as comparison-based sorting techniques, which means they reach the final outcome, which is the sorting the set of values that is given to them by comparing values. Okay? If this is greater than that, then swap the order, if you remember from bubble sort. Okay? Or in the case of quick sort, when you pick the pivot, everything to the left of the pivot has to be less than the pivot, everything to the right of the pivot has to be greater than the pivot. So you have to compare. How would you actually swap the elements if you cannot compare them? Okay? So comparison-based sorting techniques are interesting because there's so many variations of them. And what we will see is that we will prove that for a comparison-based sorting technique, the lower bound is n log n, which means you will never be able to come up with an algorithm that will perform better than n log n. Okay? I mean as the asymptotic order. I don't mean the constant beside n log n. For example, between quick sort and merge sort, quick sort will always win. 90% of the cases will win. Will have the smaller constant. Okay? Now, but that's the same asymptotic order, it's n log n. What I'm talking about here is that you never beat n log n. You never come with an algorithm that is doing comparison-based sorting in n, for example. Okay? Or log n, for example, alone. That is not possible. So, to study comparison-based sorting techniques, we will focus on the comparison because that's the main thing that gets done there. Okay, what do you do in sorting except comparing values? Nothing. Okay. Oh, swapping perhaps, yeah, but sorting is really the thing that you do a lot, or at least that is guaranteed that you need to do, because if the values are already sorted, you're not going to do any swaps, but you're still going to compare the values. So comparison, the comparison itself, is this element less than that element? This if statement that exists in every comparison-based sorting algorithm is the one that we're actually going to use to study the behavior of the algorithm itself. Okay, because it is the one that gets executed most compared to swapping, for example. Okay, so what we're going to do is we will drive a lower bound by counting the comparisons and see how does it fare. Okay, if the comparisons are n log n, then obviously you've done n log n steps. Okay. Now, let's go back to insertion sort. Okay, so what you have here, if you remember from the early days of computer science education, if you remember insertion sort, I divide the input unsorted list into two parts. One part I considered sorted, and this is the one in green, and one part that is not sorted, and this is the one in blue. And I grab one element at a time from the front of the unsorted sublist, and I find its correct location and insert it in that location in the green list or in the sorted list. So for a loom by itself, in the first line, it's sorted because an array of one element is sorted by itself. When I grab the -1 and find the value for it, the location for it, it's going to become before the 4, so I put it before the 4. And that's why, by the way, it's called insertion sort, if you remember, because you insert every value you pick from the front of the unsorted list in the correct location in the sorted list. That's why it's called insertion sort. Okay? Now I grab the 6, put it after the 4. I grab the 5, put it before the 6, and this keeps going on. I grab the 8 and put it before, after the 6, which means it's going to remain in its place. And then I grab the 3 and I will put it before the 4, and then I grab the 7 and put it between the 6 and the 8, and I grab the 2 and put it before the 3. I grab 1, put it after the -1, and grab the 0 and put it between the -1 and 1. Okay, and now it's done. So you see, everything we've done here is comparison of values. I am comparing the value at the front of the unsorted list, which is the blue list, with all the values in the sorted list. Okay, for example, when we picked, if you check the fourth line from the bottom, which is where the blue starts with 2, 1, 0. Okay, 2, 1, 0. You pick the 2, and I compared it to find its right location. I compared it with 8, with 7, with 6, with 5, with 4, with 3, and when I compare it with -1 and I find that it's greater than -1, I put it in front of -1. So it becomes -1, 2, 3, 4, and so on. Okay, so this is what I'm referring to as comparisons. And the code for this, again, I would iterate, from I equal to 1 all the way till the end of the array, and then I would iterate in the sorted list, which is starting from I -1 all the way till the beginning of the array, which is j equal to 0 or greater. Yeah, so that's j will be 0. So j starts from I -1, which is the last element in the sorted subarray, all the way till j equal to 0, which is the first element in the sorted array. And I compare the value that I retrieved, which is a of I, with a of j, and I shift as long as it is a of j is greater than value. Okay, and then when I come out from this inner for loop, I actually put the value in its place. So basically, the inner for loop enables me to shift the values in the sorted array or subarray to find the location that I'm going to insert what's called value here in. Now, this is just a refresher of doing comparisons, what I was just mentioning. Let's go to exactly how we're going to model comparisons. We're going to model comparisons using what's called a decision tree. Okay, so a decision tree is a binary tree that we could use to model comparisons, because a comparison is either true or false. Okay, so a decision tree also represents decisions you make, true or false. Okay, so when you're comparing two keys, you're making a decision. If x less than y, you go left, say that stands for false, and if it is true, you go right. Okay, so basically I could use the idea of decision trees. By the way, decision trees are not made to do, to represent comparisons. Decision trees are used in much sophisticated ways in machine learning and data science and big data and so on, but we will use it for that purpose, to model the results of our comparisons. Since the comparison is based on an if statement, an if statement is either true or false, then let's do that modeling using a decision tree. So let's look at the insertion sort, the example we were considering now. Okay, I will just work with the simple case where I have an array of 3 values, x, y, and z. I don't know who is bigger and who's smaller. But let's think about the comparisons, because we would like to count them. So what you see here is a decision tree. As you see on the edges that comes out from these boxes, it says yes, no, yes, no, and yes, no. So that's a decision of true versus false. Okay? Now, when I start, I don't know who is bigger and who's smaller the first time I run the algorithm. So all possibilities in terms of the final order of the sorted set of values, the three values x, y, and z, are listed inside the box or inside the rectangle in the node. Okay? And above all these listings, so in the first one, you have 6 of them. I'm just going to circle it for you in red. So this one that is circled in red are all the possible final outputs. So it could be that x is smaller than y and y is smaller than z. It could be that x is smaller than z and z is smaller than y. It could be that y is smaller than x and x is smaller than z. It could be that y is smaller than z, smaller than x. It could be that z is smaller than x, smaller than y. It could be that y is smaller than, it could be that z is smaller than y, smaller than x. Okay? All the possible outputs I could ever see from just 3 values. So I start with the given sequence to me x, y, z. Now, what I'm going to do, if you remember from insertion sort, I will compare the 2 elements, a of 0 and a of 1, because I will assume that the first one, x, is in the sorted subarray, and yz is the unsorted subarray. So I will compare y, the first element at the front of the sorted of the unsorted subarray, with x, which is the only element in the sorted subarray. So I'm basically comparing a of 1 with a of 0. Now, if a of 1 is less than a of 0, then I need to bring the y before the x, because what I'm looking at is x, y, z. So if y is less than x, that results in a true. So I will follow the yes edge, and y will be placed at the beginning. So it will become yxz, which is what you see inside the box at the top. There are 2 areas, a small area that says yxz. I'm just going to label it here with blue. Okay, this, and what you see inside the box are what are the possible outputs going forward. So it could be that y is less than x and x is less than z. It could be that y is less than z but z is less than x. It could be that z is less than both of them, so z will become will come before the y, and y will still be before the x. What I know for sure now is y is before the x, but I have no idea about the relation of x and z being the smallest value or not. Okay, which one is smaller, z or y would remain the smallest. Okay, that's if I get a yes. Now, what I'm going to do, I'm just going to follow the yes track first. I'm going to compare A2 with A1, because now A2 is going to be the front of the unsorted list, which is the z, and A1 is the first one I will compare with from the sorted list. So if z is less than x, that turns to be true. What that means is z will come before x. Okay? If that is less than x. So for sure now x will move to the last location. And I have 2 possibilities. Either it's yzx or zyx. I need to figure that out by comparing a0, which is that, with a1, or sorry, a1, which is that, with a0, which is y. If z is less than y, the final output is going to be zyx. So I'm going to label that with the orange color. So this is the final output I'm talking about now. Now, I started with XYZ way at the top of the decision tree. And based on 3 successive true answers, comparing first Y to X, and then comparing Z to X, and then comparing Z to Y, I ended up with the final sorted output, which is ZYX. But there are other possibilities, okay, which is listed now in the decision tree, and I hope by now you got the idea what we are doing. I'm comparing 2 elements. I am listing the elements I'm comparing by indices under each box. And based whether it's yes or no or true or false, I have reached to one more part or one more piece of the final answer, because I know now the location of one element, where to move that, whether to keep it in place or move it because it's smaller than another element I was actually comparing it with. Okay, now, so for any given output, just that we make this very clear, for any given actual output, like the numbers 7, -1, and 2, you're not going to exercise all of this tree. You're not going to go through all of this tree. You will follow one specific path from the root all the way till one of the leaves. Okay? For example, -1, -3, and 5. So it should be -3, -1, 5. Okay? So you'll be probably following something like, yes, no, yes, and then you will reach to an answer. Okay, so every one of those passes from the root to the leaf is a sequence of decisions you are going to pass through because of the specific values given to you. But what this represents are all the possible comparisons for all combinations of 3 values. And we could easily, write another one or generate another one using software for 5 values or 10 values. Obviously the tree will be much bigger, because this tree does not represent a specific execution of values. It represents all combination of 3 values, x, y, and z. It could be that x less than y less than z. It could be that z is less than y less than x. It could be that y is less than x less than z. It could be y, z, x, and so on. Okay, and this is what you see at the leaf of this tree. All the possible outputs, given that you have 3 values. But again, you will exercise one pass along this tree from root to leaf based on the actual values you assign to x, y, and z. Okay? Now here is the question. How many permutations of x, y, and z we have? It's going to be n factorial. So if 3, it's going to be 3 factorial, which is 1 by 2 by 3, which is 6. And that's actually what you see here in terms of the number of leaves. You have zyx, yzx, I'm reading it from left to right, yxz, zxy, xzy, and xyz. 1, 2, 3, 4, 5, 6 permutations. Okay? Now I hope the idea is now clear. Why are we using decision trees and how to understand this decision tree. Now let me read this. It says a comparison-based sorting algorithm can be viewed as an exercise to find the right permutation that has all the values sorted in the desired order. Yeah, makes sense. Okay, what a sorting-based algorithm does is basically tell you which one of the leaves is the output, if you'd like. Okay, which one of the leaves is the output. Now, each algorithm based on comparisons can be viewed as a proceeding by making branches in the tree based on the result of key comparisons. I already clarified this, so I hope now you got the idea. Now here is the thing. The depth of the deepest node represents the longest sequence of decisions taken by the algorithm. Okay? The depth of the deepest node. If you look at this tree, I'm going to put it for you in the next slide, and you look at the comparisons, first of all, the tree is not balanced. So based on the number of comparisons, either you do more or less, because you receive the items as input in the array, in the input array, in certain order. Okay, So it could be that the order is helping you in sorting the array because it's already ordered. So the number of comparisons you're going to make is going to be much less because values are already sorted or partially sorted. Okay? So if you look at the further away node or leaf from the root, that will give you the maximum number of comparisons you can ever do. Okay? Now, I'm interested not in the deepest node, I'm interested in the shortest distance to travel from the root to some leaf. Why? Because I'm interested in the best case, and the best case means less work. So less work means smaller number of comparisons. So what is the smallest possible number of comparisons I could ever do, starting from the root to reach to the closest leaf to the root that could possibly exist? Okay? This is the decision tree I was just telling you about. If you look here, you will notice that sometimes it takes us more decisions to reach to a final answer, and some other times we take us less. For example, to reach to ZYX, you need to go through yes, yes, yes. But to reach to XYZ, you gotta go no, no. So you're doing less number of decisions. Obviously, there is a reason why, because you're already given XYZ in the proper order in this case. So X is less than Y less than Z, so all what you had to do is to check that X is less than Y and Y less than Z. Okay? Now, and similarly also, by the way, Y, X, Z, we go through yes, no, which is again two decisions only. So if I say, can we do better than this algorithm, then this means, or translates to, can I do a smaller number of comparisons than what I can currently do? So I have to check the smallest number of comparisons. So for 3 values, the smallest number of comparisons is 2. Okay? The biggest number of comparisons is going to be 3, whether it's yes, 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 or yes, yes, no, okay, or no, yes, yes, or no, yes, no. It's all 3. Okay? So the smallest depths depend on the number of nodes. Okay? A binary tree, I'm sure you're saying why. This is why. A binary tree of height n can store at most 2 to the n minus 1 nodes. Equivalently, a tree with n nodes require at least log n plus 1 levels. So again, what does that mean? Let's look at the last bullet. Hopefully it's going to be clear. Now, decision trees are by definition binary. It's true or false, true or false. So we're really talking about a binary tree here. A binary tree, according to its invariant, can hold at most 2 children. So if I tell you that you have n nodes, say 100, and if you can only put for every node two children, left and right, in how many levels can you store the 100? Well, it turns out if it is actually balanced, then it's going to be log n plus 1 levels. Okay? Now the other way of thinking about it, if I tell you the height of the binary tree, you can tell me what's the maximum number of nodes it can store, because it's storing 2 nodes per level for every node. So it goes 1, 2, 4, and so on. And each one of the 4 will have 2 coming out. So it's going to be 4 by 2, so it's going to be 8, and so on. So a binary tree of height n can store at most 2 to the n minus 1, or if you like height h, can store at most 2 to the h minus 1 nodes, at most. That's if it's full. There is no empty slots in the binary tree. Okay? So these are 2 kind of mirror image observations. If you believe that a tree with n nodes will need log n plus 1 levels, I'm assuming here I'm saying at least. Obviously, there is there's another scenario where it's completely skewed. It's like a linked list. So, n nodes would require n levels. But if this is a balanced binary tree, it's going to be log n plus 1 levels. Okay? And then we can reverse this. We say, okay, if I give you the height, can you tell me at most how much it's going to store? And the answer is yes, it's going to be 2 to the height minus 1. So the question is, what does this relate to our initial question, which is, can we do better? Well, it turns out that the minimum height we're after is going to be log n factorial. Now, why log n factorial? N factorial is the number of combinations we could ever have for an array of some size n. So if n is equal to 3, we said it's going to, there are 6 possible combinations or permutations of the values for an array of size 3. So if I'm given an array of size 3, x, y, and z, the output will be 1 out of 6. If I'm given an array of 4, the output will be 1 out of 4 factorial. If I'm given an array of 5 elements, the output is going to be 1 out of 5 factorial permutations. Okay? So we have in a decision tree for sorting based algorithms, the leaves are always going to be n factorial. Okay? So the minimum height to have the n factorial leaves is going to be log n. It cannot be less than log n. I mean log n factorial, okay? It cannot be less than log n factorial, because I have the n factorial in the tree, okay, as a minimum in terms of the number of nodes. Well, obviously there are other nodes above the leaf all the way till the root, but if I just think of the leaves, I have n factorial of them. And since this is a binary tree, I need at least log n factorial to store the n factorial leaves. Okay? Now, that's at least. Okay? So the height of the decision tree is a lower bound on us. We cannot get it, squeezed shorter than log n factorial, because where are we going to store the n factorial leaves? Okay? So again, if you're not really confident about what I'm saying here, refer back to the previous slide and understand the relation between the number of levels and the number of nodes. Because here I'm not saying exactly, I'm saying at least minimum height, okay, is going to be log n factorial. So let's find an upper limit on log n factorial. Okay? Which means let's find an upper limit on n factorial. First. So, n factorial is 1 by 2 by 3 by 4 by n minus 1 by n. I want to find an upper limit. I'm just going to do it in a naive way. I'm going to convert all these terms to n. So n factorial is for sure less than n to the n. Okay? It's n by n. N by n by n by n by n by n, or n by n by n by n times. So it's n to the n. So n factorial must be less than n to the n. Obviously, common sense mathematically, that's true. Let's find a lower limit on n factorial. Okay? Again, n factorial is 1 by 2 by 3 by 4 by n minus 1 by n. So what I'm going to do is, again, I'm doing it here by intuition. It's quite intuitive mathematically. Just to find a quick lower limit, it's going to be the following. I'm going to throw away the last half of the terms that makes up n factorial and keep the first half. So I'm going to keep from 1 all the way till n by 2. Okay? And then I will, raise up all of them to n by 2, which means n factorial has to be greater than n by 2 raised to n by 2. Okay? So, which means n factorial has to be bounded between n to the n and n by 2 raised to n by 2. So we said it's going to take log n factorial. Okay? So let's replace the n factorial with the lower bound for it that we have found, which is n by 2 to the power of n by 2. That's the best case, because the lower bound will be the best case. So if I solve this, or I do a simple manipulation, you know, I will take the n by 2 to the side, and it's going to become n divided by 2 multiplied by log n by 2. I can do that, you know, logarithmically. But you see, this is n log n. This is n log n. That's why we say this is a proof that I cannot do better than n log n for comparison-based sorting. Okay? I hope I can take your questions now, but obviously, you know, this is a one-way communication. So if you have questions about this, ask me on Piazza, so we can actually, you know, settle things down, because I know this is a big leap in terms of proofs, but it's not. It's actually, there's a lot of common sense intuitive things here. The starting point is to understand that we have n factorial combinations, possible combinations of outputs. Given that we don't know the output, but we know the number of cells in the output. We don't know that, you know, what is the real output, but we know that it's going to be three values in the input array, and consequently we know from that the output will be 1 out of 6 permutations or combinations of values. And then we move on to the binary tree that we're using, the decision tree, to argue that to store in this binary tree n factorial leaps for our possible outputs, we'll have to have at least log n factorial levels. And this is coming from the fact that if the tree is not skewed, and we are having 2 children per node, all the way from the root going down, we know for a height of some edge how many nodes at most we can store, which is the 2 observations I had earlier. And from there, the rest of the proof just follows. Now, is this disappointing? I'm not sure if it's disappointing to you or not, but the thing is, for comparison-based sorting, you cannot do better than n log n. What if you want to do better than n log n? Well, it turns out actually, if you know something about the data, if you know some information about your data, maybe you can do better. But you need to know about the data. You need to know what kind of data you're working with. So here is another sorting technique that is not comparison-based, and it will do really nice. It will actually do it in O of n, believe it or not. But it has one big caveat, which is you gotta know about the data you're working with. You have to understand what you are getting, or you have to have an expectation, a correct expectation about what data you are going to see. Obviously, this is not the general case. Okay, this will work, for example, for if you're storing age, because people's age will vary from 0, say, to 120 or 130 years old. Okay. It might also work for postal codes, because you will know the variations. But if you're talking about a bank balance, then that will not be applicable. Okay, so let's see how this works. How can you actually sort without comparisons? How can you know that this has to come first and this has to come next or last without comparing? Okay, so this is called bucket sort. Okay, the assumption is we have uniformly distributed data, and also it is nice to actually know the range of the data. Okay, so the input numbers are uniformly distributed from 0 to 1, and I have size n input. Okay, I will divide my range into n equal subintervals for the number of items I'm going to get, and I will distribute my inputs into what we can call buckets, and then I can sort within the buckets if that is necessary, depending on how we do it. And when I'm told get me the answer, I will go through the buckets and retrieve the values. I know this sounds like science fiction, so let's move on to the example. Here is the example. It's as naive as you can ever imagine, okay? Or probably as you cannot imagine, okay? Now, what we are going to do is that we are going to establish ranges for the input. And when we get an entry, we are going to put it in the bucket that is responsible for holding values within this range. So let's say this bucket, which I'm going to highlight in with the color red, will hold values between 0.1 and 0.2. So every time I get a value between 0.1 and 0.2, I put it in there. So I got 0.12, I put it in there in bucket 1. I get 0.17, I put it in there. Okay, that's when I'm inserting the values, or when I'm getting the values like as an input. So say my input was just a list of these values. So the first one I see is 0.12, I put it in bucket 1, and then 0.17, I put it in bucket 1, and then 0.21, I put it in bucket 2, and then 0.72, I put it in bucket 7, because bucket 7 is responsible for the range from 0.7 to 0.8. And then I get 0.94, and bucket 9 is responsible for the range from 0.1 to 1. So I put the 0.94 in bucket 9. And then I get 0.23, I put it in bucket 2, and 0.26, I put it in bucket 2, and 0.39, I put it in bucket 3, and it goes like this. So I have distributed the content of my input into buckets. Every bucket is responsible for a specific range. Now we could also, generalize this idea to any kind of data where we have knowledge, a prior knowledge about the data. For example, let's apply it to strings. Okay, let's say you get a string of names, Ahmed, Hussein, Mona, Huda, and so on. So I will create bucket 1 for letter A, bucket 2 for letter B, bucket 3 for letter C. All the words starting with the letter C will go into bucket 3, and goes like this. So when I'm getting the names, I will scan the input from left to right. With every string, I will see its first letter, and based on the letter, it will go to a specific bucket. Now, I didn't sort yet, I'm just distributing the data. Now, after I'm finished with the input, putting all the input in the buckets, I go and scan the buckets from the first one to the last one. So first I will see the A bucket, so I output all the names inside. And then the B bucket, so I output all the names inside. And then the C bucket, and I output all the names inside. I'm not doing any comparisons. I'm doing distribution, and then scanning and outputting. Okay? Now, when will this work? First of all, you have to know something about the ranges, because you gotta say that I have a bucket for letter A, and a bucket for letter B, and a bucket for letter C. Okay? So you gotta know that you're working with strings that starts with letters. That's number one. Number two, in order for this to work correctly, you have to have equal distribution of values. So the number of letters or words that will start with A should be approximately equal to the number of words that will start with B, should be approximately equal to the number of words that will start with C, should be approximately equal to the number of words that will start with Z, with D, and so on, and with E and F and G and so on. Okay? So you don't have one of these buckets having 90% of the data and the rest is empty. So as long as the data is uniformly distributed, the chance of getting any value is the same as the chance of getting any other value. And as long as you have a prior knowledge about the values you are going to work with, so you can create the buckets appropriately, then this will work. Now within a bucket, you have choices. Okay? You could do some kind of sorting. So if you do, quick sort or merge sort, this is not going to be n log n, it's going to be k log k, where k is much, much smaller than n. Because what you're going to have in one of these buckets is just much smaller subset of the total input. Okay? Now, or you could put a bucket inside a bucket. When you go to the bucket A, you can then put another buckets inside it for the second letter in the alphabet, or sorry, in the input word. So if you have like Ahmed, So you're going to put it, the first letter is A, so you put it in bucket A. Now inside bucket A, when you go in there, you will find a linked list of buckets as well, following the same idea. Now the second letter in Ahmed is H, so you're going to go to bucket H, and then you put Ahmed in there. Okay? And you can even add a third dimension of buckets as well. But the point is, we're not comparing values. There is no comparison at all. We distribute the values into buckets, and then we get the values from the buckets. And then we are done. Okay? So when you say sort here, there is no comparison. You just go and scan the buckets and output the result. So this is going to be 1N for scanning the input, okay, and 1N for scanning the output or retrieving the output. And depending on what you do inside in the bucket, either you put another bucket, so it's going to be another K inside, or if you sort inside the bucket, it's going to be K log K. Okay, so this is the idea of bucket sort. It's an example of non-comparison based sorting that's O of N. But again, this will work only under certain conditions. So by this we finish the analysis. I hope you're happy by now. And let's look at some fun algorithms, okay, and data structures. So the first one we're going to look at is ranking algorithms. Okay, you cannot take an algorithm course, you know, in this kind of year or era or whatever without learning about ranking algorithms. Okay, you all open your laptop or your cell phone, your tablet, and you go to Google and search. So let's see how do these, or specifically Google search engine works. It's a class of algorithms called ranking algorithms for page ranking, and Google obviously is the most successful, implementation or innovation in this area. So let's see the idea here. So it didn't used to be always like this. So I'm old enough to tell you that in the early days of the internet, when I used to search for, say, software design patterns, I used to get crochet patterns. Okay, so anything that has patterns, including textile patterns and fabric patterns, and anything that has the word patterns in it. Okay, so web searches used to be, or web search engines used to be quite naive. Okay, the historical way of doing it was actually developing this piece of software called the bot that search engine companies used to code or build, and this bot will go around collecting pages from the internet, storing them in a database, and when you actually search for something, it all boils down to using the like SQL operator to actually retrieve pages that has words that are similar alphabetically to what you typed. So if you write design patterns, you get everything related to design patterns, including crochet patterns, So this obviously was frustrating, and you're lucky you didn't see these days. You search for anything useful and you got lots of crap. Okay, and actually it was so bad because people used to create web pages that were completely ridiculous, and they would use the keywords in the HTML to gain themselves some visibility in the search results ranking, even though their content is quite poor. Okay, and then next, after many years came Google. So let's understand the Google ranking algorithm. Now this actually algorithm is called the page ranking algorithm. So when you talk about page ranking algorithm, you're referring to Google's algorithm, or you're referring specifically to Larry Page's algorithm, which Larry Page is the co-founder of Google. And he did this actually algorithm, he invented it as part of his PhD thesis. So he was doing PhD in Stanford, and this is where he came up with this idea. And by the way, this algorithm actually appears on Google financial statements. And currently, the last time I checked, I think it was 2 years ago, the last time I checked, it was valued as this much money, which is pretty interesting because this would be like the most expensive algorithm that was ever invented by any human being. Okay, from the early days of the logarithmic guy who gave us the word algorithms. Okay, so that's pretty interesting by itself. So something that this is the algorithms actually can worth money. Okay, and this is an example of something that worth really lots of money. So let's see what is this all about. Okay, now here is the first idea you need to understand. Okay, the page ranking algorithm is based on the notion of popularity. Okay, what does that mean? Let's say you have your own page on Twitter or on Google, whatever, cloud, or on Facebook, okay? And you're interested, or in LinkedIn for that purpose. And you're interested in a specific topic. So you keep searching for content online that is related to this topic. And out of the tens or hundreds of pages you come across, you like just a handful of pages or websites that are really providing useful information. So you go and start referencing them in your homepage, or perhaps you write an article on LinkedIn saying, I've read about this topic there and there and there, and these are the best websites that talk about this topic. Okay? Now, if you just do it once and you're the only person who's liking these websites, well, that's not really important. But if a lot of people keep referring to the same website over and over again, what that means is these websites are really valuable. They have some useful information because everyone is referring to them. Okay? So the idea that this algorithm is based on is that when a page is referencing another page, it is referencing that other page because there is some useful information in it. This is what I try to illustrate here in the figure at the bottom right. If page A and page B and page C are all referencing page D, that means page D has something useful. Whoever is authoring page D, he's doing a good job. He's presenting useful information. That's why people are linking to him. Okay? They are saying, oh, see this article about so and so. Okay? So the hyperlinks in this way of thinking becomes like a trust reference. When you are actually referencing that page, this means you trust it. You find the content valuable. Okay? So if we can download all the pages on the net and count the cross references, who's referencing what, and we will have some really valuable information because we will know which page is referenced most by everyone else who's interested in that topic. Okay? It's like the author of page A is giving his vote by referencing page D. He's giving his vote to page D. He didn't give it to page X or page Y or page T. He gave it to page D. So he's like voting for that page. And same thing, the author of page B, he's also voting for that page. And that's why he referenced it. That's why he's citing it in that sense. And same thing for page C. Okay? So the hyperlinks here are more like, trust references, and not just, or trusted reference, and not just a hyperlink. So the basic idea goes like this. Every time some page is referencing another page, we will give the referenced page, which is page D here, a value. Let's talk units. So we will give 1 unit or 1 point to page D because page A is referencing it. And then we will give also 1 point to page D because page B is referencing it. So each page referencing another is giving it 1 point. Basically, it's vote. Okay? So in terms of rank, since no one is referencing page A, rank of A is 0, rank of B is 0, rank of C is 0, but rank of D is 3 because it's being referenced by A, B, and C. Okay? Now this is where it gets interesting. When the author of page D, who has rank 3, references another page, this guy, the author or the content of page D, is very valuable because it was referenced by 3 other pages. Now, if the author of this page, page D, decides to reference another page, we're not going to give that other page F 1 point due to the reference from D. We are going to give it these points or these weight. Because if A, B, and C find D valuable and D find F valuable, then F must be more valuable than D. So F will get 3 points or rank, or D's rank through or get 3 points through D, and it will get 1 point through E since E's rank is 0. Okay? Now, and if we extend this idea to the whole internet, covering all the references between all the pages, obviously this will take lots of time, and you know, you can actually look up online for some interviews with Larry Page about his early research. He used to leave this kind of computations for days to run to be able to actually figure out which page is ranked highest in any specific topic. Okay, but this is the idea of the ranking. But now there is an issue. What if the author of page A references another page, in this case page G, along with referencing page D? We are going to treat, or we're already in this model treating the reference as if he's voting for the page he's referencing. He's saying this content is good. If you have come to my page to read about topic X, then also see this page because this page is good. Now, if he links to 2 pages, this means he's saying this page is good and this page is good as well. So he's distributing his vote between 2 pages. And consequently, we will not give 1 point from A to page D, we will give it a half, because he split his vote, or he is referencing basically 2 pages. So he split his votes between those 2 pages. And that will propagate upwards, so now D will be 2.5 and F will be 3.5 because it gets 2.5 from D and 1 from E. But we have a problem. It's very common on the net that people reference each other. Okay? Not done in a malicious way, but it is common. So according to our model, if we try to compute the ranks of pages based on references, with the existing of what's called back references, that people will reference each other backward, or creating this loop of references, we will ultimately, go into a situation where all the ranks will be plus infinity, because we will, I will add a 1 because D is referencing C, so I will add a 1 to C, and then C is referencing B, so I will add a 1 to B's rank, and then B is referencing A, so I will add a 1 to A's rank, and then A is referencing D, so I will add a 1 to D's rank, and then D is referencing C, so I will add a 1 to C's rank, 1 more 1, and this will go on forever. Okay? So the model is nice. It is basically outsourcing the evaluation of web pages to the crowd. So people evaluate content, and if they like it, they reference it, and consequently, if we count the references, we can find the ranks of pages, and then we can sort by rank. Everything is working fine up till now, okay? Up till the previous slide. But now we have a problem. We have to fix this, because this will basically break the model. This will break the algorithm. We will go into an infinite loop. And we cannot prevent people from referencing each other. So, we have to live with that, and we have to find a solution to this problem. And this is really, the most innovative part in Larry Page's algorithm, which is the random surfer model. Okay? It's a very, very subtle and very elegant way of thinking about the behavior of people when they visit pages, and the utilization of that in solving the infinite loop problem in page ranking. Okay? Now, the main observation this is based on is that if you have a set of connected pages, every surfer who visits one of these pages will not visit all the pages. Right? Think of it common sense wise. If you're looking up a topic, say for example, MongoDB or Node.js or Android development or iPhone development, you're going to get a lot of pages, and you will surf some of them, and then you will stop and do something else. You will go and read a book, you'll go out, you will get bored, or you will think of another topic and jump somewhere else. Okay? This is obviously common sense observation, but it actually plays an important role in what we are going to describe. So what he says is the following, or what the model says is the following, the random surfer model. Every surfer starts in some page related to the content he's looking for, follows some link in this page to a related page, and keep doing that for a while and then stops and go away. Okay? He's not going to visit all the pages. So given a page, we will talk about the probability of leaving that page and teleporting to other unrelated page or switching off his laptop for that purpose as being alpha. And consequently, the probability of staying and following one of the links in the page is 1 minus alpha. Okay? Now, let's move on. So let's say we have these pages. We will start our model by all the pages having the same weight. Okay? And the sum of all the weights should be 1, because this is probability, remember? So it will actually make our calculation simpler, and it kind of fits within, probability theory, the odds of being there or not being there. Now, what I'm going to do is I will compute the probability of having a visitor on a page by following links. For example, how many ways can I go to D? I could be on A and go to D, or I could be on B and go to D, or I could be on C and go to D. But I cannot go from D to B because there is no reference. These references are actually hyperlinks, HTTP hyperlinks. Now, there is another way actually I could go to D, to jump directly to it. Like I know the URL, so I just type it. Okay? So in terms of the number of ways people can be at D is go from A to D, go from B to D, go from C to D, or just jump directly to D. Okay? There is also something else, which is someone who would be far away from from D, let's say being on X, and X is connected to A, so he goes from X to A to D. Okay? I'm just introducing the idea, so hold on. So, let's say this is my world of pages, a little bit more complex than the previous slide, and a little bit more links or hyperlinks, just to get a sense of the differences between the pages in terms of rank. Okay? I'm going to ask the question for every page. What is the probability of a surfer being on a specific page, let's say page D, after one move? So after one move, he can be on C and move to D, he can be on B, move to D, he can be on A, move to D. But obviously E, he cannot go to D. Okay? So let's again ask the question. What's the probability of the surfer being on page D after one move? So that will be from C to D, or from B to D, or from A to D, or from E to D. How come he can go from E to D? He can go from E to D if he jumped directly by typing the URL. Okay? Not by following the link. Now, the probability of going from C to D is going to be the following: 0.2 multiplied by 1 minus alpha multiplied by half. How is this computation? 0.2 is the chance of being there initially, because we have 5 of them. We have 1, 2, 3, 4, 5 pages. So the chance of being on any page is 0.2. Multiplied by 1 minus alpha, which means teleporting to C from D. Alpha is jumping away from this system of references, not following the references. Following the references is 1 minus alpha. Now, since C is referencing 2 pages, then the chance of actually going to one of them is half. You either can go to B or go to D. So the chance of being on C is 0.2. The chance of following the references is 1 minus alpha. The chance of going to D is you multiply that by half, and the other half is for going to B. Okay? Now what about going from B to D? the chance of being at B is 0.2. Multiplied by following the link, the chance of doing that is 1 minus alpha. What about A? 0.2, just like C to D, A to D, 0.2 is the chance of being at A, multiplied by the chance of following the link, which is 1 minus alpha, multiplied by the chance of going to D, not E, is half. What about the last one? In our world, there's only these 5 pages. So he was in E and he jumped directly to D. So the chance of being at E is 0.2, and the chance of jumping directly to D is alpha. Okay? So, again asking the question, what's the probability of the surfer being on page D after one move? It's what is displayed at the bottom. We'll add all of these probabilities. Okay? So that will be 0.37. Okay? The probability of a surfer being on page D after one move is 0.37. Okay? Now, the alpha here, it's not trivial. Larry Page goes into a lot of detail about it. I'm not going to do that. I'm going to skip it. You can read his paper. I'm linking it at the end of the lecture slides here. But I'm showing you the basic idea. But that's just, this is not the whole thing. This is just calculating it for D. We are going to calculate it for all of these pages. Okay? And after we've done that, this will become our values. Okay? What is computed here is the chance of reaching to one of those pages after following one reference. And you were one reference away and you followed the reference to that page, to each one of those pages, or you jump directly to that page. Okay? From any one of the other pages. But that's just for one move. We're going to compute it from 2 moves and 3 moves. So we will go into like a very intense kind of computation to figure the rank of the pages. Okay? Notice that in his model he is actually using the references in his probability calculation. So still the references are there, but they are now weighted by the chance of actually going to that page. And the chance is split by the number of references. That's why when we calculated it for C, to go from C to D, we said you can go either, if you're going to follow the references in C, that's a chance. And there's another chance you just go away. Okay? But if you follow the references coming out from C, you have 2 options, either to go to D or to go to B, because that were the references inside C and HTML. So his model is still relying on the existences or respect the existences of the references, but he is weighting it by the chance of being there or of going there to every one of the pages from all the connected pages at 1 level and at 2 levels and 3 levels away and 4 levels away and 5 levels away and so on. Okay? So this is Larry Page contribution to the history of computer science, and it's a very impressive algorithm. Okay, it solves a very complex problem, and this is why Google now is what it is. Now, a final note, if you actually compare the random surfer ranking, which is at the top left, and the count ranking, which is what we described earlier, you will notice that the rankings are not much different. Okay? And this is also another beautiful thing about the random surfer model, is not giving you different really results, it's just solving the infinite loop problem, and it gives you more or less the same results as we have seen before. Okay? And you can verify the numbers in relation to each other. And again, to stress the point, we're not going to just do it by asking what's the probability of being at page D given this set of references or configuration of references and staying 1 page away from D. We're going to ask the question, what is the chance of being at page D while you were 2 pages away from D, or 3 pages away from D, or 4 pages away from D? Okay? Now, I mean by 2 pages away from D, maybe C is connected to X and Y, and you were at X, and then you will go from X to C and from C to D. Okay? Or you were at Z, and you will go from Z to X to C, then to D. So we'll compute all of those. Obviously, the further away you are, the less chance you arrive to D. Okay? If you think of how you navigate pages online, you don't follow references in a single page or from a single page and just keep clicking on links from one page to the next like endlessly until you reach to the hundredth page down in your traversal history. Okay, people don't actually traverse pages like this, and even if they do, it's even when we count it here, it's not going to be changing the numbers a lot, because the ones that are farther away, the probability of them reaching to D is less, okay, because of the nature of the probability calculation. But still, this is considered in the model, and the rank is calculated accordingly. By this, we finish the page ranking. I will give you a link at the end of the lecture slides to Larry Page's research paper, and if you get too excited, you can read about it online. There are many actually simulations and videos that explains and simulates this. Now let's move on to the last and final topic in this course, which are the data structures. The data structure I will start with are tries. Very entertaining, very amusing data structure. Okay, a trie is a tree. Okay, it's also called, by the way, in some textbooks, radix tree or prefix tree, and it's mainly used to store strings. Okay, and the utility of it is to search for a prefix or a whole string in a super fast way. Okay, and also in a very compressed way. You could alternatively use a database, but if you don't want to use a database in your application just to store a bunch of strings, this is going to be an ideal alternative. Now, a trie is a tree. It's composed of what's called trie nodes, okay, and each node contains a flag to indicate whether it's the end of a word or it is not the end of a word. Okay, now each node will contain a character that points to another trie node. So this is not a binary tree, this is a general purpose tree. It could grow in any fashion based on the strings stored inside it. Okay, and by default, the trie node flag that tells you this is the end of the word or not is set obviously to false, because you have to set it intentionally or explicitly by using some code to true. So here is an example trie after inserting the string 10. So notice at the bottom of each trie node there is a flag that says false or true. If it's true, this means this is indicating it's the end of a word. Notice that I'm storing every letter or character in the string. This is not a number, this is a string, by the way, as it's contained between double quotes. Every letter in the string in a trie node. So to construct this string 10, I have to start from the root, follow the 1 reference to the 0, follow the 0 reference to the end of word trie node. Let's insert something else and see how will this build up. So if I insert 31, I also start from the root. I will insert the 3 and link it to a 1. This is going to be the child of 3, and link that to a trie node that says this is the end of the word, okay, or indicates this is the end of the word trie node. So when I'm constructing 3-1, if I'm like to retrieve it, I will start always from the root and follow the 3 to the 1, and then when I find that the next after the 1 it's an end of word trie node, I will just return 3-1. Let's insert 200. Again, I start from the root. I will insert the 2 in the first root trie node, and then a reference to the 0, and then a reference to another 0 for the second 0 in the 200, and then finally a pointer to a end of word trie node. Inserting 53, again I start from the root trie node. I will insert the 5 because there is no 5 there, and then I insert the 3, and then the end of word trie node. Inserting 20, I will follow the 2 that exist in the root trie node because I've inserted, remember, 200 before. Okay, and now I will follow this to the 0, and from the 0 I set, from the first 0 I set the flag in the node after to true. This will enable me to reconstruct 200 and will enable me to construct 20, because the try node after the last letter in the word I'm inserting should be set to true. So now I have set, and I'm going to highlight it here with red, I have set the flag in the try node following the first 0 to true to indicate that I can construct a 20 as well as 200. Now let's insert 40. I'll insert 4 in the root try node and then a 0 and then end of word. Let's insert 60. I will insert 60, then a 0, then the end of word. Let's insert 90. I will insert 90, then a 0, then the end of word. Let's insert 103. So I had already a 1, so I would follow that to the 0. Okay, so 1, 0 was inserted before. That's the first one I started with, or the first string I started with. And then I will insert a 3, setting the end of word flag in the 3 that I'm going to highlight here with the red color to true, and then I insert another one after it and also set it to true. So I can construct the 10 this way and also the 103, or the string 10 and the string 103. What about 150? Again, I will follow the 1 to the child of 1, which is the one that has the 0 from before. I will insert the 5 and then the 0 and then the end of word try node. Okay? Let's insert 75. Again, I'm going to follow the 7, follow the 5, and the end of word. Let's insert 15. I will insert the 5 and I will modify the true flag in the 0 to be this one to be true, the end of word flag to be true, so I can actually retrieve 15. Let's insert 40. I have this one 4. I will come here, and I already had, because I was inserting 400 before, I have changed this to true, okay, so that I can do, or I've inserted this and I've pointed this here so I can follow the 40. Okay. What about 31? I had the 3 here. I'll insert the 1, and here is the end of word try node. Now the question is, why is this useful? It sounds like a complicated way to store strings. Well, first of all, we use it if we are not interested in keeping the strings in a database. Okay, that's number 1. Number 2, and more importantly, there is something about it that makes it quite unique compared to a database, which is our ability to search for complete words and at the same time our ability to search for prefixes very, very fast. Okay, this is almost like some kind of a search tree where when you make a decision you ignore everything else. So if I'm looking for 31, okay, I start at the root level and I pick the 3 and I ignore everything else. So I'm ignoring pretty much 90% of the 3, and then I move to the 1 and I'm ignoring the rest that exists in this second level try node. Okay, so we can search for prefixes. Prefixes means I give you the beginning of a word and you tell me which words match. Where do you see this? You see it online all the time. Okay, you see it when you're searching in any website. You type, for example, Cairo, you type CAI, and then you get a list of candidates: Cairo, Cairo City, Cairo Capital, New Cairo, and so on. Actually, New Cairo is not a good example here, but you get a lot of things that start with CAI, okay, including Cairene and Cairo Times and so on, and Cairo Street. Okay, now how you can actually do this fast using a try? This is why this is a common data structure, in interview questions, because it is used a lot in online in many web frameworks to speed up what's called the autocomplete feature that exists in text boxes. Okay, so it has its good usages. I'll continue on. Insert 120. We already had the 1, so now I need to insert the 2. That's labeled over here. Okay, and then the 0, and then here is the end of word flag. Now I have listed here for you instructions or explanations of how we do the insertion, how we do the search, and whether for a prefix or a whole word, and how we do the deletion. So I already described that, and for the deletion, obviously we'll have to be careful not to delete common prefixes. So if I have ABC and ABG, and I would like to delete ABG, I cannot just delete everything ABG, I will just delete the G, but I will keep the A and the B because it's shared between ABG and ABC. That's the only thing or caveat you need to take care of when you do deletion. And I have mentioned to you here some examples of trie trees or radix trees. Okay, they're very popular. So that's why I'm kind of introduced to you the idea, and you will see some tutorials about how you go about the insertion, deletion, and search. Okay, and here are the references for today's lecture. Okay, from the Wikipedia entry on PageRank. If you scroll down at the bottom, I mentioned to you that I'm going to give you a link to the Larry Page original research. If you traverse all the way to the bottom of the page, and the page on this Wikipedia entry, you will see a reference to his page or to his research, and you can read the whole paper that he worked on.